Today we're going to look at sets, power sets, and cardinality as indicated by the title screen on the screen right now. So how the session will work, I'm pretty sure Shay went through it a bit in the morning. I just had my own slide because I didn't realize he was doing it as well. I want it to be highly interactive, so I'm going to quite often be inviting people onto the stage to talk. If you don't want to talk, if you don't want to enable your mic, that's fine. You can just type in the chat, but I want to be able to invite people onto the stage. I'm going to divide up the session into its components. So in this particular session, it's going to be sets, cardinality, power sets, and then injective, surjective, and bijective functions. We'll finish off with countability. And for each of these sections, I'll briefly explain the facts and the concepts, and then I'll invite people to ask, answer, and discuss the questions, or if they have any questions, onto the stage. Yeah. So how can I see the Discord as well as the slides at the same time? Let's try this. Okay. Right. So, sets. Let's get started. So sets. A set is a group or an unordered list of items that usually share a similar property. You can chuck stuff into a set. It's like a list, but the only thing is that there's no order to it. It's just grouping stuff together. There are standard sets in maths that we can include without having to define them ourselves, and this includes natural numbers, integers, rational numbers, real numbers, imaginary numbers, and complex numbers, and you can see the symbols for them on the side over here. Other thing is, a subset is a set inside another set, which means all of its elements are also elements of the other set, which would be called a superset. For example, we can see in this one with the numbers here that every set is a subset of complex numbers, and rational numbers is a subset of real numbers, integers are a subset of rational numbers, and natural numbers are a subset of integers. So that's how sets and subsets work. Now we're just going to look a bit at Aye, Captain. Nice. Good joke, Shay. Nice. Cracking the fun ones. All right. So set notation. So set notation is pretty much like what we've been using in math and then a lot of other modules as well. So you basically put elements inside a set inside curly braces like this. If you want to say a specific element is inside a set, you put like this symbol that looks a bit like an E. And you put that symbol and put X is in A. And that means it is part of that set. By the way, the things inside the set, they're called elements, by the way, in case I didn't make that clear earlier. If you have two sets and you write A equals B, that means that A and B are equivalent sets, meaning they have all the same elements. This symbol here, it's called phi, and it denotes an empty set. So if a set, like the one at the top where I didn't put anything inside it, has no elements inside, you can represent it with phi, which is an empty set. Then we have the and symbol, which in latex is called cap, and then the or symbol, which is called cup. And then this bar, vertical bar, is one that you can read it as such that, so it often describes like properties of a certain expression. So you'd be like X such that, and you'd say stuff about X. And finally, we saw what subsets were in the previous slide. If you have A and then this C symbol at the bottom, B, that means A is a subset of B, aka all of the elements in A are also elements of B. Cool. Does anyone have any questions about set notation, or are we good with it? Happy with it? What is going on in the chat with real? Okay. All right. We can argue about all right, cool. All right, next. Now here we've learned some like operations and things we can do with sets. So these are like similar to like maths, but their meanings are different. So the syntax is the same, semantics are different basically. So the Cartesian product is basically multiplication, which it's not multiplication, but it uses the times sign like multiplication, and it merges two sets together. And basically, the way this works is you form a set of pairs, or like triples if you're merging three sets, for example. And these pairs or triples or whatever are tuples. And the key thing to remember here is with a tuple, order matters. So you have to have a fixed order. It's not like a set where you can just chuck everything in and it doesn't matter the order. So you'd have like, if you're multiplying A with B, or Cartesian producting, I should say, then you'd always have to put the element from A first and then the element from B. And that's represented in this mathematical notation, which, as you can see, is actually using a lot of the set notation that we learnt above. Then once we have Cartesian product, similarly, now you can also just have to the power of n, and that means the same as basically a times a times a times a as n times. And that's basically like your Cartesian producting the same set multiple times. You'd write it using this notation. And it's the exact same principles that apply. Then finally, we move on to difference. So the difference of two sets. So a backslash b would mean a subtract b, which means you'd result the elements of a that are also not elements of b. And the thing we're going to learn now, the complement, is something you can use to describe this. So a to the power of c notation means the complement of a, which is basically all of the elements that are not inside the set A. They can be anywhere else. They could be in any other set or in the universal set. It doesn't matter. As long as they're not in A, they're included in the set complement of A. And yeah, that's Cartesian product, difference, and complements. Okay, so that's all I had on sets. We're going to move on to power sets, cardinality, and all of that later. So I just wanted to give the questions on sets now. And this is the bit where you can request to be invited onto the stage. And I'll invite you on if you want to ask some of the questions. First question is, what is the set given by the Cartesian product of 1, 2, 3 and 4, 5, 6? Does anyone want to be invited onto the stage? Pretty sure you can request. No? Wait, show request. There we go. Invite to speak.
Hiya. Can you hear me?
Bonbons has been invited to speak. Are you able to?
Can you hear me?
Are you able to join?
Can you hear me now? Hiya.
Yeah, I can hear you. Hi. Yeah.
Yeah. Wouldn't it be 1, 4, which is the first element, 2, 5, and then 3, 6?
1, 4, 2, 5, and 3, 6.
Yeah.
That is some of them. Yeah, but there is some more. So you can have. It doesn't have to necessarily be exactly the first, second, and third. With the first, second, and third corresponding. You can have like 1, 4, 1, 5, 1, 6.
Oh, okay.
2,
yeah,
5,
I get
3,
that.
5, 3, 4, 3, 5, 3, 6, basically, and that would be the entire. Yeah.
Okay, that's clear. Yeah, thanks.
Cool. Nice one though. Right. So yep. So it's every combination basically, and next question. Using set notation, define the set of rational numbers. I'm just gonna check in the chat what's going on. So, oh, there's a lot. Yeah, you did it. You did it, Shay. Good job. That's power set. It's yeah, I think the chat's okay right now. Okay, so basically, now does anyone want to have a go at the second? Oh, the second question though, where you're defining using set notation the set of rational numbers. So it might help. I mean, that is a good one. You can just write Bonbons has just written x such that x is in rational numbers, so that is actually correct technically. Yep. But if without just writing it's in rational numbers, which is actually a very valid solution. Should have thought of that. How can we represent it? Oh yeah, rationals are Q not R. So yeah, it's not actually R. R would be real numbers. So rationals, yep, there we go. Fred has it there. Yep. So it is I and J. The only thing I'd say about your solution, Fred, is that I would need to be an integer, not a natural number. If I is a because you can have negative rational numbers as well. So normally we say the numerator is an integer and the denominator is a natural number. The other thing you'd need to add to your solution, Fred, is that j cannot be 0 because you can't divide by 0. So yeah, if you're not able to see the slides, you need to click watch stream on the thing. Right. So integers and natural numbers, basically integers would allow negative numbers and natural numbers would not. And natural numbers allow 0, which is why you need to specify that j is in natural numbers, but also subtract 0, basically. Yeah, so Shay, your solution with -1 over -2 is in fact a rational number. However, that's just the same as writing 1 over 2. So you wouldn't, like, that's why we won't classify it as a solution. So we say one of them, it can be the numerator or the denominator, has to be within the set of integers, and the other one will be in the set of rational numbers. What you have to just make sure is the denominator, you specify that it can't be 0, no matter which set you put it in, because it'll give you a divide by 0 error. I can see the chat is now. Does everyone understand? Not always. Could you explain notation further? I'm a bit confused. Bonbons is asking, could you explain notations? So what about notations are you confused about? Would you want me to what notations? Okay. Okay. Are you on about like the notations people have put in the chat? The answer to the question, yeah. Okay. Basically, where did the message go? Okay. So, this message, this solution. So in this solution here, or actually no, Fred has done a better one here. Basically, this is the solution here. Okay, in this one, what it's saying is I and j. So do you know that rational numbers can be represented as a quotient, right? So it's a division. So you can have anything that you can represent as a fraction is a rational number. That's the definition. So if you have two like things, one of them is in a set of integers and the other one is in a set of natural numbers, you can represent any fraction, and therefore you can represent any rational number, but you just have to make sure that the denominator is not 0. Does that make sense? That's all we're saying over there. I think n includes 0, does it not? I don't know. That bit I'm not too sure on. Do you need to specify I as being... Okay, yeah, that is a good question. I had that same question. Never odd or even is asking, do you need to specify I as being divided by j? You do not, because you can't do that in set notation. We're kind of identifying the syntax here rather than the semantics. So we're not saying what we're doing, we're just saying how we can define a rational number, and all you need to define a rational number is a numerator and a denominator. So it's a good question. We're kind of only defining the syntax of a rational number here rather than the semantic. But yeah, I thought we were told it wasn't or on our course. Okay. If like I can, are people understanding? Hang on, like should I move on or like do the majority of us get it? Let me create a poll. Okay, cool. All right, I think the majority say we should move on. Okay, so if you still have any questions, we'll answer them at the end, but we're going to move on for now. Okay, so next question being, how can you, again, using set notation, define the set given by A subtract B? Okay. It's n such that n is in A and n is not in B. Yeah, perfect. That is exactly it. Or you could have said n such that n is in A and also n is in the complement of B, which would define basically the same as not B. All right, cool, good. Good one, Shay. Right. How can we simplify? So we have expression here. A is a subset of B and B is a subset of A. How can we simplify this expression? A and B. Not quite. Yep, that's right. Not A and B, but yeah, bonbons, Fred, you will have it right. A is equivalent to B. A equals B is the correct answer. Good job. Okay, so next thing. We're going to move on. Don't worry, Shay, you've been great so far. Okay, so next thing we're moving on to is cardinality. So, cardinality is basically sets can be defined in like 3 categories. For now, we'll call them 2 until we get onto countability later. So they're either going to be finite, so they have a limited, like fixed number of elements inside, or they're going to be infinite, like natural numbers, integers, rational numbers, and real numbers. They're all infinite sets. Cardinality is just the word that describes the size or the number of elements in a finite set. When we're talking about finite sets, we can use them as said at the bottom, we can use them for infinite sets, but we're going to look at that later. So in the context of finite sets, they literally just describe the number of elements inside the finite set. So it's basically like writing dot length if you were to use a list. And basically to show the cardinality of a set, you put modulus bars around the set you are trying to output the cardinality for. And just a side note, that singletons are defined as any set with a cardinality of 1. So one element being inside the set means it's called a singleton. Right, so let's do some questions on cardinality. I did say I was going to invite people to the stage, but I think the chat works as well. What is the cardinality of this set on the screen? Can you tell me what the cardinality of this set is? Fred says 3. Other Fred says 3. There are 2 Freds. Oh my god. Okay. And yep, everyone's saying 3. That is correct. Yep. So we're doing the cardinality of the largest set, and therefore the cardinality is 3 because this is a set of sets. So the magnitude would be 3. Good job. Yep. 1 plus 1 plus 1 is also correct. Good job. All right. Evaluate this. So what is when you evaluate this expression, what do you get? 1. Fred says 1. Shay says 0. 10 says 0. 0. Someone put 3. Okay, 0 is the correct answer. Good job. Because this phi, remember, is a notation for the empty set, which contains 0 elements. Therefore, the cardinality is 0. Next thing, power sets. So, It is assumed that every set has a power set, and a power set is the collection of all the possible subsets of that set. So any possible subset you can make from a set would be included in the power set. And that's basically the set of power sets. It's a set of subsets of a set. The power set of A is denoted by this symbol here, and unfortunately I don't think there's any latex command that allows us to write this weird looking P. So I just had to copy and paste this image from the slides. Oh, someone's done it. Great. I wish I knew this before. What is 10? Just WP. Was that literally just it? Okay. WP, I'll remember that. Okay. So, a tip when writing power sets is to go up in cardinality. So, start with the sets that have a cardinality of 0, like basically the only thing is the empty set, and then follow it up with the singletons, which remember are sets with a cardinality of 1, and then keep going up until you do all the combinations and you reach the original set itself, which is still included in the power set, by the way, in case you were asking. So, yeah, I guess I kind of just answered this question. Is A a subset of A? Yeah, it is, because it's included in the power set of A, so itself is a power set of itself, and it's included in the power set. All right. Can I invite someone onto the stage for this one, or do you want to still use the chat? Up to you guys. Would anyone, if you want to be invited onto the stage, just send me the invite. But no requests are being shown, so I'm assuming it will be in the chat. Okay, let's open up the chat. Oh, invite to speak. There we go. Someone invited to speak.
It was an accident, but I'll answer it anyways.
Okay.
So it would be first of all, it would be a set including the empty set, and then it would have 1, 3, and then 5, and then 9, and then 1, 3, and then 1, 5, and then 1, 9.
Yeah.
And then do I keep going?
I get you. So now you're going with the doubles and then the triples, and then you'd end up with, what's the final set you end up with?
Right. Yeah, exactly. So it's just gonna be a whole bunch of combinations of this set, and then the end subset would be 1, 3, 5, 9 itself.
Yeah, good, correct. That's right. Yeah, I'm not gonna make you go through the entire thing. Good job. All right, cool. So that's the power set of that. I hope that kind of explains, if you were confused, how you'd get a power set of a set. And all right, next question. What is the cardinality of P of A if if A modulus bars is equal to n? So look at this expression. I'm gonna try and not read it out because I want you to be able to know what the signs mean. But what is the cardinality of the power set of A? Let's look at the chat. Yep, so 2 to the n. 2 to the n is correct. So, yeah, good. How is it 2 to the n? Because, well, if you look at, say, a set with let's say a set with 2 elements, just 1 and 2 in it, right? So you have the empty set, and then you have 1, then 2, and then 1, 2. That's 4 elements in the power set, and we had 2 in the original set, so 2 to the 2 is 4. And therefore, the cardinality is just 2 to the n. So, I don't know, can you imagine one set power set? Yeah, that. Or yeah. So 1 to the 1 and 2 would have power set 5, 1, 5, 1, 2, 1, 2. So 1, 2 would have the power set, empty set, 1, 2, and 1, 2, which means it has 4 things, and therefore it's 2 to the n. That's one example, but it's not 2 to the n plus 1, basically. Does everyone understand that? For a set of 3 elements, the power set would have 9 items. No, it would be 2 to the 3, which is 8. Yeah, as Fred's saying, it'll be 8. Cool. All right, let's move on now. So that's how you determine the cardinality of a set of a power set by the cardinality of its set. It's just a 2 to the n relationship, exponential. All right, let's move on now. Okay, what is the set for the power set phi? So this is basically a reverse of what we did before, but can anyone tell me what the set would be for this power set? I kind of actually accidentally used this as an example because it was on the screen, but yeah, that's correct. Just 1, 2. Cool. You just look at the number of just look at all the unique values in this, and yeah, the set would just be all the unique values minus phi because you wouldn't include that. Okay, next thing. I hope everyone understood this stuff with power sets and cardinality before that. We're now going to move on to injective, bijective, and surjective. So these are types of functions. So A to B is surjective. So I think surjective is the easiest one and it's the least restrictive one in my opinion, but that's not like facts, that's just how I like to think of it. So what it means, this notation, I'll read it out. For all y's in set B, there exists an x in set A, given that f of x is equal to y. So all it's saying is if there's an element in the codomain, right, there is at least one element in the domain that maps to it. So you can think of it as pre-image and image, or domain, codomain. The gist of it is pre-images map to images after the function is acted on it, or elements of the domain map to elements in the codomain after the function's applied. So basically, if a function is surjective, there's nothing in the codomain set. Okay, yeah, do you understand codomain? Basically, codomain is the output set. That's a good way of thinking about it. And the domain is the input set. So inputs map to outputs. Therefore, elements in the domain map to elements in the codomain. Yeah, exactly. That's right. So codomain is f of x and domain is x. Yeah. So that's what domain. Yep. Does everyone understand the domain and codomain? Similarly, other terminology I'm going to be using here is image and pre-image. So an image is the element in the codomain, and the pre-image is the element in the domain for that image. All right, cool. So every element has at least one pre-image. So if you don't get anything from the surjective, if you don't understand the other bit, just remember that every element has at least one pre-image. At least one. And then let's move on to injective. So injective means for all x for all x's and y's that in the set of A, such that if f of x is equal to f of y, then x has to be equal to y, basically. And if that's true, then it's injective. And basically what that's saying, if the mathematical notation is kind of confusing, because yeah, it is, I agree, it's confusing. Every element in the domain maps to exactly one unique value in the codomain. Pre-image. Don't worry, we're with you, Manch. Pre-image is basically the one in the domain, and then the image is what that pre-image maps to. So a pre-image maps to an image, and the pre-image would be in the domain, the image would be in the codomain. Does that make sense? So just some value in the domain is the pre-image. Normally you refer to pre-images, we're talking about a specific value. So you'd say like an element in the codomain, you'd say that element's pre-image. I don't know if it's correct to say the domain is full of pre-images. But yeah, you can think of it like that. Yeah, I guess so. Yeah. So the pre-image is an element in the domain. Yeah, if that helps, think of it like that. But yeah. Yeah, that Kieran is, yeah, there you go. Yeah, Kieran and Fred have it there. So that's what I was trying to say. You can't, it's not like the domain is full of pre-images. It's only a pre-image if there is an image. And similarly, it's only a pre-image if there's an image, yes. We'll just look at that. Because not every element in the domain has to map to an element in the codomain, and vice versa. Not everything in the codomain has to map to something in the domain, or has to be mapped. Sorry, and therefore, that's why I wouldn't say it would be totally correct to call all of them pre-images and all of them images. Okay, cool. Oh, it's Kieran's birthday. Happy birthday, Kieran. Let's get happy birthday, Kieran, in the chat for Kieran, please, guys. All right, great. I hope you have a great day. All right, so basically, every element in the domain maps to one unique value, and if that was an easier way to remember it, every element has at most one pre-image. So the previous one, surjective, was every element has at least one pre-image, whereas in injective, it's every element has at most one pre-image. So that's a good, easier way of thinking about it. Cool. And then finally, once we have surjective and injective established, we can move on to bijective, which is basically injective and surjective. So if you have a function that's both classified as injective and also surjective, then we call it as bijective. It's the intersect of injective and surjective. You can think of it like that. Kieran's birthday is all the talk today. I hope you have a good day though, Kieran. Anyway, basically, every element in the domain maps to exactly one element in the codomain, and every element in the codomain is mapped to exactly one unique domain element, aka it's a one-to-one mapping, basically. All right. I'm going to move off injective, bijective, and surjective. So does anyone have any final questions or thoughts about injective, bijective, and surjective before we move on? Makes sense? Cool. React to Shay's message that says makes sense if you agree. All right. I'm confused on the difference between injective and bijective. Okay. Injective and bijective. Basically, if you understand injective and bijective is basically injective and surjective. So you know how we looked at surjective at the top, and then we looked at injective. So surjective means every element has at least one pre-image, and injective means every element has at most one pre-image, and therefore bijective is just both of them, right? So injective and surjective. Therefore, every element has exactly one pre-image. It's a one-to-one mapping. It's just injective and surjective. If you have both of those true for a function, then you call it bijective. And yeah, does that got it now? Thanks. Cool. Yeah, everyone understands everything. Cool. Lots of reactions to Shay's message. All right, cool. I'll move on now then, if everyone's happy. So that's injective, bijective, and surjective. Why does bro type in latex? Is it correct to say if f of x is surjective, then inverse is injective? So let me go back. So if f of x is surjective, so meaning it has at least one pre-image, and is the inverse injective? I think so. That does check out in my head. I think that's correct. Yeah, I think that would be correct. Yeah, but don't hold me on that, because I would need to give it some more thought if I was to answer that with the proof or something. But yeah, I think that roughly checks out. All right, so finally, the last topic on this. We'll get to more questions with the injective, bijective, surjective after we get this bit, which is basically we're using the concepts we just learnt. So basically, there are 3 kinds of sets. We introduced it as 2 kinds of sets earlier when we were talking about cardinality, but the truth is that there are actually 2 kinds of infinities. So one of them, we looked at finite and infinite. We know what finite is now, that can push to the side. Let's look at countable, finite, infinite, and uncountably infinite. So what does it mean to be countable? What does the property of countable mean? So countable means if there's a bijection between it and the set of natural numbers. So if a set has basically a one-to-one mapping between itself and natural numbers, then it can be classified as countable. So looking at countably infinite sets have a one-to-one relationship with the set of natural numbers, and therefore we say they have the same cardinality as the set of natural numbers. So you might have thought that cardinality was only something you can use to describe the magnitude. So that is true, but the reason why we call it cardinality and not magnitude is because it's slightly different to that definition. So you can use cardinality to describe infinite-sized things as well, but you just can't obviously pinpoint a size to it like you can with a finite set, but you can say it has the same cardinality as another known standard set. For example, if something has the same cardinality as a set of natural numbers, we call it countably infinite, and that's exactly what the definition of countably infinite means. Same cardinality as the set of natural numbers, or if you want to think about it, it could be a one-to-one relationship between the set of natural numbers and itself. And then uncountably infinite sets have different cardinalities. Basically, they have any cardinality as long as it's not the same as the set of natural numbers. And basically, they do not have a one-to-one relationship with the set of natural numbers. For example, rational numbers. Fred, what? Okay. Rational numbers. Is it possible to go through some exam-style questions? Yeah, we will go through some questions on this, and yeah, some of them can be, some exam-style questions, yeah. Full cardinality considered. Right, okay. We will go through some exams, don't worry. We'll go through some questions after this. So, yeah, rational numbers. Can anyone come onto the stage, because it's going to be quite a long thing to type. Can anyone come onto the stage and explain why rational numbers are considered uncountably infinite, going by the definitions that we just learned? Put your request for the stage. Have a go. Someone, come on, have a go. Why is rational numbers considered uncountable, whereas integers, for example, are considered countable? Anyone? Okay. Same. No. You're thinking of integers. Integers and rational numbers are separate, yeah. So in integer, you can do the zigzag mapping, but rational numbers... No one wants to come onto the stage, and okay, that's fine. The reason why rational numbers are uncountably infinite is because, obviously, yeah, I'm enlightening you, don't worry. Obviously, they can't be mapped to the set of natural numbers, and the reason is because you can have an infinite number of decimal places after a number. So think about decimal numbers. Decimal numbers are considered rational numbers. Well, most of them. You know, obviously, I'm not talking about pi and stuff. Oh, that is countable. Almost all real numbers. Rational numbers are uncountable or countable. Zigzag mapping. Isn't that for integers though? Like you can have like I'm talking about real numbers, not numbers represented on the computer. You can have an infinite amount of like you can keep going into decimals, and like you can have 1.222222222, and that would keep going, and then you could have 3 point whatever. Oh, right. Yeah. My bad, guys. Real numbers. Real numbers are uncountable. Rational numbers are yeah, sorry. Okay, my bad there. My bad. I meant real numbers. All right. Real numbers are because of the zigzaggy, yeah. Real numbers are uncountable and rational numbers are countable, as well as integers, natural numbers, whatever. So real numbers are the uncountable because you can keep going into decimal places and you could infinitely just keep going. So that's why they are considered as uncountable. Real numbers, not rational numbers. I'll correct that in my presentation before I send it in the chat. Let's change that to real numbers. Okay, cool. Does anyone? Thanks for that correction. It's good that we have people to correct me if I'm going wrong. So that's good. Anyone confused about this or have any questions, or should I move on? Can you explain it? I'm confused about different between countable and uncountable infinite. Okay. All right. So basically, countable infinite is basically an infinite thing that you can kind of relate to natural numbers, right? So you know the set of natural numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. They are integers, right? But only the positive ones. So if you can kind of map whatever infinite set, you can agree with me that natural numbers are infinite, is an infinite set, right? Because you can keep on going with natural numbers and you just keep going. There would be no end to it. So that's an infinite set. Now, if you have a set that you can, map to this set of natural numbers using a one-to-one mapping, so each element in your set is mapped to one element in the natural number set. That means you have a countably infinite set, basically. It's a bijection. Does that make sense, bonbons? Why would rational numbers? Yeah. Basically, I made a mistake on my slide with that one. It's not rational numbers. It's real numbers that are uncountable. Rational numbers are indeed countable because they are just like a quotient of an integer and a natural number. Therefore, they are countable, but real numbers, they are not countable. They are uncountable. Rational. In fact, I'll change it right now just to prevent any confusion. Okay, let's go here. Rational numbers, real numbers, and okay, present. Okay, there. And that should be the correct one now. Okay. Cool. Where did my slides go? Okay, right. So, are we all happy with this now, or does anyone have any more questions about the countable and uncountable infinities and stuff? Okay, chat. Here we go. I think I got it. Thanks. Still hard to wrap my head. It is kind of hard to wrap your head around it, and to some extent, I'm still making mistakes with it. I still put rational numbers here instead of real numbers, but yeah, that's corrected now. But it is kind of hard to wrap your head around infinity, because infinity we think about it as something endless. So how can you have two types of endless, right? That was what I was finding hard to wrap my head around, but there are some good videos. And I think just remember the definition. I don't think we'll be asked too much like conceptual or theoretical questions on uncountable and countable. I think just remember the definitions. And because most people can't wrap their head around two different kinds of infinity, so that's fine. All right, now the much awaited questions. So I do actually want to like invite people onto the stage if they want to answer some questions. So, are finite sets considered countable? Oh wait, am I not screen sharing? Did I stop screen sharing? Oh, my bad. Screen share ended. Okay, I'm going work. Okay, there we go. All right, can you see the screen now? Yeah, okay, cool. All right, so are finite sets considered countable? Yes. People are answering yes. Oh, yes. Invite to speak. Someone wants to speak. Come on to the stage.
Yes.
All right, yeah. That's good. That's good. Cheers. Nice. How can we use countability of sets to prove that not every language is regular? So this is kind of relating back into theories of computation and regular languages. How can we use countability and like that property to prove that not every language is a regular language? Love that from you, Banj. Nice. But yeah, any idea anyone wants to speak? How can we use countability of sets to prove that not every language is a regular language? Yep, it is a Paul Levy reference. Yep, Paul, good old Paul. We actually learned this proof at some point, I'm pretty sure, but yeah. Levy, Paul Levy. 10 people are typing. Damn, okay. There always exists a word that is not accepted. Yeah, but how can you prove that? How can you prove that there exists a word that's not accepted? Right. Well, I have the answer to this actually on the next one. I haven't drawn out a full proof, but I've made it in words that is easily understood, and hopefully you can understand it afterwards. Let's move on to this one. I'll reveal the answer to that question after we do the rest then. So if sets A and B are both countably infinite, is it true? Like, is A union B and also A intersection B, are they also countably infinite? What do we think? Yes. Yes to both? Yes? Okay. Yes. All right. Does anyone want to come up and explain their reasoning for that, though? Their reasoning behind... In fact, I'm going to pick on someone who said yes to say what the reason. Why do they think that everyone that... if A and B are both countably infinite, why is A union B and also A intersection B countably infinite? What happened? Right, Shay.
Because my voice isn't on the recording, but okay. You have to like paraphrase it. But basically, because one set's countably infinite and the other's countably infinite. If you're doing an or, like a disjunction, then it's kind of concatenating the sets. So it's still like countably infinite. I can't describe it. It's because you can like plot it in a 2D graph.
Yeah.
And then
what about specifically for the intersection though?
Oh, for the intersection, it's you can, because you know one's countably infinite. The intersection will always be a strict subset. No, it will always be a subset of one of them. So it will always be less than the maximum cardinality.
Can I give you, so I have the set of negative numbers, and I have the set of positive numbers. Can we agree that they're both countably infinite sets?
Yeah.
What is the Is the set A intersection B still countably
Right.
infinite?
So no, it will be at most countably infinite.
It will be at exactly. That's the correct answer. Yep. So with A intersection B, it's at most countably infinite, but not necessarily. So we can't deduce with an intersection that just because both the component sets were countably infinite, that the resulting set is countably infinite. So it only works with a union. Cool. Thanks, Shay. Thanks for talking. All right. Did everyone understand what I said there? Our conversation with Shay. I feel like I'm running a podcast here, inviting people to like talk. So, for everyone that said yes to both, you can't deduce that A intersection B will give you a countably infinite result just because A and B are both countably infinite. That only works for union. Would the power set of countably infinite set be uncountable? Out of interest. The power set. The power set has how many elements in it? The power set has 2 to the countably infinite. Right. Yeah, I don't think it's countably infinite because it would be. I don't know if you can. I kind of understood what Shay is talking about, but 2 to the countably infinite. I don't think that means it's countably infinite. Does it? I think it would make it uncountable if it's 2 to the power of some countably infinite set. So yeah, because it won't exactly map. So if you have a countably infinite set, and now you're producing like 2 to the n amount of infinity, basically. It won't be never odd or even asked. Just to confirm, A union B will be uncountably infinite. No, not uncountably, countably. So just to reply to never odd or even, countably. Yeah, that's correct then. Yeah. So A union B will be countably infinite if A and B are both countably infinite. However, A intersection B might not be. Correct. Cool. Everyone good with this question, understands it. Let's move on to the next one. If A is countable and B is a subset of A, then is B countable? Can we get some people to... Remember, if you answer, I might ask you to explain your reasoning. Shay's got an answer straight away. Okay, right. Let's pick on someone who perhaps hasn't talked yet. I'm going to invite to stage. Let's invite Fred. Fred, are you happy coming onto the stage? Nice, cool. All right. Can you explain why you put yes and why you think that if B is a subset of A and A is countably, I meant countably infinite there. I hope you got that bit. And then what would B be countably infinite?
Oh, because if it's a subset of A, it's either the same or smaller. So.
Exactly. So it would be countable, definitely, right?
Yeah.
Yep, exactly. Good job. Thank you. Right. As Fred perfectly explained there, B as a subset would have to be at least the same size or smaller than A, so it cannot be bigger. And therefore, B would have to be countable. Now let's reverse this question. Good job, Fred. And let's ask, if A is uncountable and B is a subset of A, then is B also uncountable? Can we get some responses? If you respond, you might be called on to talk your reasoning here. So if A is uncountable and B is a subset of A, then is B also, can we say that B is uncountable as well? We've got Bonbon saying not necessarily. Okay. Anyone else? Any other responses? Does that have a definite answer? What do you mean by a definite answer? Like, yes or no? It's at most uncountable, right? Yeah. So everyone, not necessarily, it's at most uncountable. Yep, that's all correct. Good. I'm going to call upon 10 to explain your reasoning. You are correct. Not necessarily. Why did you say not necessarily? Have you got the invite? I can't see. is hello. Hi. Thanks for joining us. So, what are your thoughts? Why did you put not necessarily? You're correct. Can you just explain your reasoning?
Well, he's like one element.
I'm going to turn my sound up. Sorry, what do you say?
So if you imagine B to be one element, then it's not uncountable.
Exactly. Yeah. So you just disproved it by an example. Yeah, that's perfectly fine. Cool. Yeah. So B has to be smaller, so it does not have to be uncountable. Thank you, there, Ten. It can be any value. You could literally just have it with one element. It could be no elements. It could be like something countably infinite. But at most, people who are saying at most uncountably infinite, you'd be correct. Yeah. At most, it would be uncountably infinite. Cool. Great stuff. You guys seem to have a good grasp on the concepts. Okay, cool. Someone asked a question. But B can also be equal to A, so would be uncountable. Yeah, so that's why we're saying at most uncountable. So it could also be nothing. It could just be maybe a set that says 1 or 2. But yeah, on the edge case, we have that B being a subset. Right, Shay. That's just like. All right. Yeah, let's not be sus. Okay. So, good job. Yep. Show that the set of integers has a bijection to the set of natural numbers. How can we show that the set... So basically, what representation? How can we show that the set of integers has a bijection to the set of natural numbers? You guys showed me this thing with rational numbers before using the zigzag thingy. What can we use here to write out how they map 1 to 1? Okay, what would be an example of how they would map? Can you give me like what would map to what? Yep, exactly. So you'd have half of them mapping to negative numbers and the other half mapping to the positive numbers. I have no idea how he typed that fast either, but like, you know, that's Shay for you. Anyway, so that is how you prove that the set of integers has a bijection to the set of natural numbers. They would both be countably infinite, but just the natural number set would be double whatever you have for the integers, if that makes sense. But both of them are countably infinite. Good. Alright, this is the final question and kind of requires a bit of a proof, which I'll show you. So, let X denote the set of infinite strings of zeros and ones. Is X uncountable or countable, and why? So if you want to, like, you know, make your knowledge and foundations concrete for infinity and countable and uncountable, this is a good question to take a look at. So if X denotes a set of infinite strings of zeros and ones, is it countable or uncountable, and why? I don't remember the whole proof, but it has something to do with the diagonal. Yeah, so it is called the diagonal argument proof. Yeah, so where is Kieran saying it is uncountable? Kieran saying it's uncountable. Any other thoughts? Is an infinite string of zeros and ones, is that going to be countable or uncountable? Countable, but not sure how to explain it. Okay, alright. So I fully understand both like answers here. I understand why you might think it's countable, especially since we just did. We just showed that integers, positive and negative, can all be mapped to natural numbers, right? And it seems like that. It's like zeros and ones. When just like how we map negatives and positives to natural numbers, surely we can map zeros and ones. But I think the question lies in the particular definition. I did not put strings as a typo. So it is an infinite, so a set of infinite strings, plural, of zeros and ones. That might be a hint, but we will look at the proof for that now. So if we're done speculating in the chat, but that is the hint: infinite strings of zeros and ones, multiple strings. Okay, so we're going to look at something called the it just feels like it. So yeah, my natural instinct is to go ahead and call it countable, right? And that is what I'm pretty sure most people would say. When you just think about it, you'd think it's countable, right? Well, this is one of the examples where it's not actually countable. And that's why I thought it would be important to show that sometimes you require proofs. And this is a very specific one, but like, yeah, normally you can be fine going with your gut. But this specific case may come up in the exam, the diagonal argument, which is why I included it. So I'm going to share a different tab now. This is... Can everyone see my screen now? The lecture notes, yeah? Yep, so for all of those that can't remember the reason, etc., and can't remember the proof, this is it. So, can everyone see that? Would you like me to zoom in or make it a bit bigger? Okay. I'll just... Looks good. Okay, thanks. Thanks for the feedback. All right. So basically, because it's a set of it's a set of strings, and each of those strings can be of infinite length, it is actually uncountable. And we're going to show this by proof by contradiction. And if you're unfamiliar with that, it's basically where you assume something to be true, and then in the proof later on you go about your proof and then show how that assumption cannot be, because it, you know, creates a contradiction, hence proof by contradiction. So if there is a bijection, so we suppose by contradiction that x is uncountable. So so we're gonna assume first that it is countable. So if we assume that it's countable, then we can later on show by contradiction that it can't be. So there would be a bijection of natural numbers to x, because that's what countable means, right? 1-to-1 mapping between natural numbers and x. And this is the way they've decided to draw it out, which I think is actually quite useful. So this set on the left is the natural numbers, 0, 1, 2, 3. And as you can see, 0 is included in the set of natural numbers as well. And then the set on the right is the x. So these are the strings. So there's an infinite number of strings, and each string has an infinite number of ones and zeros. And I think now you can kind of see with this representation why we'd end up saying it's uncountable. Each of these is now mapping to an infinite string, and there is an infinite number. So if it was just an infinite number of strings, but each string is finite, then it would be countable. But because each string is also infinite, there is another degree of infinity. So f maps to natural numbers of infinite strings. Each row represents an element in x. So that's basically this. I hope everyone understands this representation. Now let's go to the proof. F is assumed to be a bijection, so a 1-to-1 mapping. But we will argue that f cannot be surjective. That's what we're going to do. And the way we're going to do that is we're going to say we define a new infinite string, which is an element in x, which cannot be in our list. And we do so by looking at the diagonal. So you can see the diagonal going across here. This is why it's called the diagonal argument. We define the orange element by changing zeros to ones and ones to zeros on the diagonal. So we just flip all the bits off the diagonal. In this picture, so if we have 1, 1, 0, 1, blah, 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 we can argue that for all n, for every single value, if we apply the function, it's not going to be equal to what we had. And therefore, if we have f of 0, it's not going to be equal to what we had originally if you look at the top. And as it disagrees on the first digit, and then all of them would disagree because it's diagonal. This one would change to a. This one was originally a 0. It would be a 1. Then this one would change, and this one would change. So it would disagree on the first digit, and the second digit, and the third digit. And therefore, you can say it's not surjective, which means it does not at least. Surjective meant, remember, there is not at least one pre-image. There is at least one pre-image. So, and therefore, we have a contradiction. We assume that it would be bijective, but we can't have bijection without injection and surjection. So therefore, if it's not surjective, we have a contradiction, and therefore X is uncountable. Now, I've gone through a lot of complicated stuff there, and like I am going to share these pages, so if you want to take a look at this later, that's fine. I wouldn't expect myself even like to wrap my head around this the first time I came across it. It took some thinking. But how are we feeling on the chat? Do we understand? Do we see what's going on? Yeah, I get it. Okay, cool. That's good. So even something like this, where you initially think it's going to be, your gut instinct tells you it's going to be countable, but it can also turn out to be uncountable. All right, cool. Now, as I promised, I will go back. Manj did request the proof for the second question we had. I'm going to go back to sharing my presentation screen. Hold on. Okay. Stop streaming. Okay, right. Can you guys see my presentation screen now? Yeah, cool. Okay. So this is just going back to the questions that we were already on the slide. But remember how I said the second question on there, how can we use countability of sets to prove that not every language is regular? Now, with this, the answer I have put here, and this is not the formal proof, because I personally, when I looked through the formal proof, it didn't make much sense because there was a lot of like notation and stuff. So I have kind of listed out in plain English here. So regexes are basically how you can define regular languages. That's the definition. So if you had a set of all the possible regexes that can ever exist, right, that set would be countably infinite. Can we agree that set, if you had a set of all the regexes that anyone could possibly make in past, present, future, it would be countably infinite, because you can have an infinite number, but you are limited by the possible number of characters. Characters would be finite. We can say that regexes, any regex can be turned into a DFA, and by Kleen's theorem, and by definition, deterministic finite automata, DFA, keyword being finite. So therefore, and then obviously only 3 operations allowed, juxtaposition and all of that. The only reason it's infinite is because there's always another regex that you can add to the set. So there's only one degree of infinity, just like with the set of natural numbers. And so this would be uncountably infinite answers to our question from earlier. Yep, there we go. So therefore regexes are countably infinite. Okay, cool. Next part of the proof. Why a set of languages is uncountably in... I've left in my latex notation that I did. Why did that not write? Okay. The set of all languages, including non-regulars, and that's a sigma, basically, notation, is uncountable, as there are no limiting rules or operations in place with its representation. When you're defining a language, right? Yeah, I'll go over the degrees of infinity in a sec. When you're defining a language, you're not constricted by any rules. Like, say you're creating a new programming language. There are no rules that you need to, apart from like the basic ones of like, it means like Turing machines and computation. You're not bound to keep it regular, basically. You can do whatever you want. And that's why not all languages are regular. And then we learned later on that we can use things called context-free grammars to define semantics. And yeah, so this set of like languages, all the languages in existence, that's uncountably infinite because we are not bound by the same rules that we are when we have to keep it regular as well. So that's why it's uncountably infinite. And therefore, once you understand these two, it's simply just said that from the proofs above, we know that the non-regular languages have to exist because there is a countably infinite number of regular languages, however, an uncountably many number of languages. So if there's uncountable number of languages and only a countable number of regular languages, that means there's obviously some languages that are non-regular. Do you guys understand the proof? Yep, makes sense. Cool. All right. Cool. Going to that was just one of the questions. Going to what you said about the degrees of infinity. I think this was in the definition. It was like natural numbers have 1 degree of infinity, and that means that it can just go up in terms of degree of infinity. I think I'm probably not too well versed in what it means for something to count as a degree, but like it's different ways you can have infinity. For example, in the previous one with the strings of zeros and ones, we had infinite number of strings, and then each individual string also had an infinite number of bits. So it was kind of like 2 degrees of infinity there, and that's why we decided at the end it was uncountable. Yeah, exactly. So if it was adding another dimension, so kind of like what I was saying with the previous examples of zeros and ones, we have infinite number of strings, and each string also has an infinite number of bits, and we said it was uncountable because there's now 2 degrees of freedom. There's another dimension there. If another dimension that is infinity. If it was, as I said before, just each string was finite, but we had an infinite number of strings, or we had 1 string or a finite number of strings with infinite bits, then we only have 1 degree of infinity, and therefore it would be countable. But because there's multiple degrees of infinity there, there was it was uncountable. Main theory limits infinity undergoes the same mathematical rules, so would be coefficient infinity. But Bonmons, you roughly understand what I meant by degrees of infinity. Yeah, I get it. Cool. And I'm pretty sure that wraps up everything. Yep, that wraps up sets, power sets, cardinality, surjective, bijective, injective, and hope you found the questions useful as well. These are some especially the last questions on the last slide were like the toughest ones you could possibly get like on an exam, like these hard proof questions. They would honestly not give you that in the real exam one. So don't understand if you found it hard. Don't worry, sorry. Yeah, thanks guys. I enjoyed learning. I actually learned quite a bit by making this, so it was helpful for my revision as well. Thank you. All right. Well, I'm gonna move to the VC now. So the VC is just under this stage, and I'm gonna be there for a couple minutes in case anyone wants to if anyone has any questions or wants to add any comments, add anything to anything I've said. And regarding the slides, they will also be posted onto the this Discord server. I'll put the slides on, and if you want, I'll also put the diagonal arguments proof on as well from the lecture slides. Thank you, man. Love you too. Right. Okay. Cool. I'm heading on to the VC now. If anyone wants to ask anything there. Thanks, guys.
Be sure to join tomorrow, guys. The full schedule is in upcoming. Tomorrow we have Talk by Freddie and Syntax of Propositional Logic by me at 11 a.m. and 2 p.m. respectively. Anyone who talked today, are you guys okay for me to post this on YouTube, onto the YouTube channel? I think it was just Manj, Fred, and James. If I'm missing anyone, let me know. Cool. Oh, nice. Awesome. Cool. I'm gonna go to the VC, I think. See you there. Oh no, oh no.
Right. Thanks guys for joining. I enjoyed that session. I hope you guys enjoyed it too.
Yeah, it was really nice. It was informative.
Very good. Let me check it recorded.
Oh no. Or it's about to be like, oh, sorry, I forgot to press